Hello everyone. We are in section 3.11 talking about hyperbolic functions. Hyperbolic functions, these are often called hyperbolic trig functions. They're technically not trig functions, although I can definitely understand the confusion because we use the trig functions as labels for them. But basically, hyperbolic functions are actually exponential functions. They involve combinations of exponential functions. The reason that we associate them with trig is because the relationship that they have to the hyperbola shape, that type of curve, is exactly the same type of relationship that the trig functions have to a circle. So the idea of sine and cosine, right, giving us x values and y values in a circle. If you think about like the unit circle, sine of an angle gives us a particular value on the unit circle. It's the same kind of thing with these hyperbolic functions on a hyperbola. So the relationships that they have very closely resemble those of the original trig functions, which is why we give them these trig-like names. So basically we're taking the sine, cosine, and tangent functions, and it looks like we're just kind of adding an h onto each of them. That h stands for hyperbolic. So the way that we would read this would be, you could say hyperbolic sine, hyperbolic cosine, hyperbolic tangent. But of course we get lazy and we don't want to have to keep saying hyperbolic blah blah blah, hyperbolic blah 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 over and over again. So typically we read these as sinh, cosh, and tanch. So basically you just add the sh sound onto each of them. So we've got sinh, cosh, and tanch, and then of course the corresponding cosecant, hyperbolic, secant, and then cotangent. So the original two, hyperbolic sine and cosine. Hyperbolic sine is e to the x minus e to the negative x all over 2. And hyperbolic cosine is e to the x plus e to the negative x all over 2. So as you can see, very much exponential functions that we're working with here. And then just like with trig, every other hyperbolic function can be found as some combination of sinh and cosh. So just like with the trig functions, every other trig function can be found in terms of sine and cosine. So a couple quick identities here that we can use for hyperbolic trig functions. If you take sinh of a negative x, that's the same thing as taking negative sinh of x, whereas cosh of negative x is the same thing as just cosh of positive x. This is also similar to the regular trig functions. It has to do with the evenness and oddness of these types of curves. And they have similar, though not exactly the same, types of identities that we can actually prove. And the proof just all goes back to these exponential functions. So we have cosh squared minus sinh squared equals 1. So you can kind of see a similar resemblance to the one that we know from regular trig. So let's start on the left-hand side here. So we'll start with cosh squared of x minus sinh squared of x. So we'll do cosh, that's e to the x plus e to the negative x all over 2 squared, minus sinh is e to the x minus e to the negative x all over 2 squared. If you FOIL these out, so you take e to the x plus e to the negative x squared, you end up getting e to the 2x plus 2 plus e to the negative 2x all over 4. And this is because you combine e to the x with e to the negative x, and the x's cancel, so you get e to the 0. And then minus, you get something very similar, e to the 2x just with a minus 2 plus e to the negative 2x all over 4. And now if we look at simplification here, so this minus, it distributes to everything over here. So we have e to the 2x minus e to the 2x. We have e to the negative 2x minus e to the negative 2x. But then we have 2 minus negative 2, so that's 2 plus 2, which is 4, over the common denominator of 4, which is 1. And so that signifies the end of the proof, because we got cosh squared minus sinh squared equals 1. So we can use their exponential definitions to derive identities and formulas for cosh and sinh. And then for the others, so this one, we can use cosh and sinh to derive any of these others. So we're going to start off with the one that we just proved. So we know cosh squared minus sinh squared equals 1. So we just proved that was true. And what we're going to do is we're going to divide by cosh squared. So we're going to divide everything in here by cosh squared, each of these terms. So that's going to be 1 minus sinh squared over cosh squared equals 1 over cosh squared. And if you look back at these definitions, hyperbolic tangent, so tanh, is sinh over cosh, and sech, so hyperbolic secant, is 1 over cosh. So we have a couple of squares here, but it's the same thing. So we get 1 minus tanh squared equals sech squared, or hyperbolic secant squared, which is exactly the relationship we were trying to prove. So you can use the exponential definition of sinh and cosh to derive their properties, and then use sinh and cosh to derive all of the others. So now let's talk about the calculus of hyperbolic functions. For sinh and cosh, we can calculate their derivatives using, of course, their original definitions. So this is derivative with respect to x of e to the x minus e to the negative x all over 2. The over 2, we don't have to use the quotient rule on this because the 2 is just a constant. We don't have a function over a function. Derivative of each of these individually. Derivative of e to the x is e to the x. Derivative of e to the negative x is e to the negative x times negative 1. So really just turn that negative into a positive, and the 2 just tags along there. And this, if you look back at the previous page, that is cosh. So it turns out the derivative of hyperbolic sine is hyperbolic cosine. And that probably doesn't come as a big surprise because in regular trig, the derivative of sine is cosine. Now if we look at the cosh function, take the derivative e to the x plus e to the negative x all over 2. We get something similar happening. E to the x we get minus e to the negative x all over 2. Now, in the regular trig, derivative of cosine is negative sine. In hyperbolic trig, this is the formula for sinh. So the derivative of cosh is just sinh. It's not negative sinh like it is for the regular circular and triangular trig functions. So derivative of sinh is cosh, derivative of cosh is sinh, and then of course the derivatives of all the others can be found using those two. And those, so we won't go through that whole process of finding those, but that is their derivatives, and you'll see that they correspond very closely to the originals. Then we have hyperbolic inverses. So sinh inverse, cosh inverse, and tanh inverse. So the original versions of these are exponential functions, so it kind of makes sense that their inverses would be logarithmic functions, because exponents and logs are inverses of each other. So these are their general formulas. We can then actually find their derivatives using just our typical differentiation procedures. So we're going to do it for sinh inverse, and then all the others I have down below, but they're all derived very similarly. So to find the derivative of inverse sine hyperbolic, that's going to be derivative of just exactly what it is. So ln of x plus square root of x squared plus 1. This requires us to know how to take the derivative of the natural log and how to use the chain rule, very much so. So, if we take that derivative, so derivative of the natural log, that's 1 over whatever's on the inside. So that's right there. Times derivative of the inside. And that's where the chain rule comes into play. So we have 1 over x plus rad x squared plus 1 times derivative of x is 1 plus derivative of the square root function, that's 1 over 2 times radical x squared plus 1, but this function also has a function inside of the square root, so we do have to employ the chain rule to this one as well. Derivative of x squared plus 1 is just 2x. So we can cancel those 2's, and not a whole lot else yet. So we have 1 over x plus radical x squared plus 1 times, let's see, this is 1 plus x over square root of x squared plus 1. So let's just give those a common denominator. So that's square root of x squared plus 1 plus x over square root of x squared plus 1. So if we combine these together, so square root of x squared plus 1 plus x over, I'm just going to switch the order of these two. It's just addition, it doesn't matter. Square root of x squared plus 1 plus x times this one, so times square root of x squared plus 1. And now look at what we have. We have this whole thing as one object cancels with that whole thing. So all we're left with is 1 over the square root of x squared plus 1. And that is the derivative of the hyperbolic sine function. And I think it's pretty interesting because you're taking the derivative of something that looks like trig, has a formula that's a logarithm, and who has a derivative that has none of those things. It's just a rational function with a root in it. So very interesting how that works out. The other formulas are derived very similarly to this.